This video is a Unit 5 test preview from my Chemistry 1 Advanced classes. Net and complete ionic equations, and maybe I should say complete and net because you got to do the complete before you do the net, are really simple. Don't make this hard, okay? Don't overthink this, all right? When you put a salt, so this is an ionic compound, we know it's ionic because it contains a polyatomic ion. That's the way I've taught you from, I don't know, several units ago to recognize an ionic compound. When there's a polyatomic ion in the formula, or it's a combination of a metal and non-metal. When you put an ionic compound in water, if it dissolves, so if it's soluble, it becomes aqueous. It becomes aqueous because it's solvated. And the process that I taught you in the last unit about solvation is that the ions separate and they get surrounded by the water. That's solvation of a salt. So when I put this in water, it's aqueous. We've identified as aqueous. This is being separated from this, or from both of these, because there's two hydroxides, okay? So what's really in water is not BaOH2, it's Ba with a 2+ charge and two hydroxides. That makes sense? A complete ionic equation is only writing out the things that really exist. Okay? Now this solid over here, this doesn't break up in water. That's why it's a solid. It's not being solvated. So what we're going to do is just break up the stuff that's ionic and aqueous. That's it. That's all you got to do. You with me? It's simple. You're breaking up the stuff that's ionic and aqueous. Got that? So in this formula, I have one barium ion. That's Ba with a plus charge. And we said that barium hydroxide, just like any salt that's solvated, breaks up and is separated, and it's solvated by the water. It's actually dissolved in the water. So this barium ion is aqueous because it's dissolved in the water. Okay? We have how many hydroxide ions? 2. So when we write that out, we're going to write it as 2 hydroxide ions. Not as OH in parentheses with a subscript 2, because we've broken them apart. Now the two hydroxides are separate things. So we're going to write it down as 2 separate things. That makes sense? Okay? Can you break this one up and write it out? Take a second and do that. Then I will come behind you and show you what the correct answer is. See if you got it right. Break this one up and write it down here. I'm going to pause the video. Okay, so I have 2 potassium ions, and I have 1 sulfate ion. Okay? Got that? Wait a minute, people are writing? You should have written already. Oh, you missed? You didn't quite get it right? Okay. All right. Do you understand your error? That's important. It's not so bad that you made an error. It's important that you learn from it. All right. Now this is not aqueous. So what do you think we're going to do down here when we write this down here?
Just leave it the same.
Leave it exactly the same. That's exactly right. Because it's not breaking up. It stays the same. And what am I going to do with this last one over here?
Break it up.
All right, you do that. Break it up. Write it down. Let's see how you did. Okay, so how many potassiums do I have over here? 2. That coefficient in front means I have 2 potassiums. How many hydroxides do I have? 2. So that's the complete ionic equation. Okay? That's all it is. Should not be hard, because this is basically undoing the stuff we did when we first balanced equations or balanced formulas, right?
You only break apart what's aqueous.
But you're only breaking apart the stuff that's aqueous. Okay? We're just undoing what you learned to do when we first learned to balance formulas. Period. That's it. All right. Now, this only is done for double replacement and single replacement reactions. You could do it for synthesis and decomposition sometimes, but there has to be an aqueous environment, and we're not going to worry about that in this class. So you only have to write complete ionic equations for double replacement and single replacement reactions. Got it? Because combustion reactions don't happen in water. Nothing's being dissolved, okay? So that's the complete ionic equation. Now, the net ionic equation, this is what's really happening in the water, right? This is what's really happening because things got broken up when you dissolve the salts. Net ionic equations are only looking at things that are doing anything. Only looking at the part of the equation that's really doing anything. Okay, that's all a net ionic equation does, is looking at the parts, showing the parts that are actually doing something. So let's take a look at this hydroxide right here. Okay, I've got two hydroxides, they're aqueous on the left, two hydroxides, they're aqueous on the left. They didn't do anything. They're the same. Nothing changed, right? So they should not be part of the net ionic equation because they're not doing anything. They're just standing around watching things happen. They're the spectators. And that's what we actually call them. These are spectator ions. Okay? All we're going to do to write the complete ionic equation is write down anything that actually changes. So why don't you try to do that? Look at this complete ionic equation, figure out what actually does change, and just write down that part. You do that, we'll come back and see how you did. Okay, if you're involved in any kind of competition, sports or whatever, you should know what a spectator is.
Yeah.
You should know who's in the game, right? All we're looking for is who's in the game. Let's look at barium. Did it change? Yeah, it changed. We're going to list barium in our net ionic equation. I'm sorry, I should have written that 2 plus. Okay, it changed from barium 2 plus, dissolved in water, to barium in a compound that's not dissolved in water. It changed. Okay, it's doing something. All right, now we just said hydroxide doesn't change. It's a spectator. I helped you with that one, didn't I? What about potassium? Did it change? No. So we're not going to include that down here in the net ionic equation because it's not in the game. How about sulfate? Did it change?
Yes.
Yeah, it changed. It changed from this being aqueous, an ion that's dissolved in water, it's solvated, to a sulfate in a compound that's not solvated. It's a solid. So sulfate did change. And that's all they have on the left side. And we already said that potassium didn't change and hydroxide didn't change. The only thing to list over here is barium sulfate. That's it. That's the net ionic equation.
Oh.
Alright.
So you just.
Okay? You want to do one more? All right. Here's a problem for you to write a complete and net ionic equation for.
And then you got my. Yeah. It was easy. Yeah.
Okay.
I can't grow.
The complete ionic equation. This is aqueous. It's ionic. You know it's ionic because it contains a polyatomic ion that's SO4. So this one breaks up. Zinc is a solid. It doesn't break up. Elements that are by themselves and not bonded to anything else don't have a charge. If you wanted to put a 0 up there, you could. Okay, but I just usually leave the 0 off. But you could put a 0 there. This one's breaking up because it's aqueous. So it's breaking up into zinc ions and sulfate ions, but cadmium over here is solid. It has no charge, it stays the same. Okay? So the complete ionic equation looks like this. In the net ionic equation, we only keep those things that change. So cadmium over here, it has a 2+ charge and it's aqueous, and it changes to cadmium that's so solid. So cadmium's changing. Sulfate is an ion and it's aqueous on both sides. Nothing happened with sulfate. It stayed the same. So we're not keeping sulfate. Zinc started out as a solid over here. It started out with no charge because elements that are by themselves don't have a charge. And over here, it was an ion in this compound that got dissolved. So zinc changed. The only thing that didn't change, the only spectator, is sulfate. And we keep everything else for the net ionic equation. The question is, how do we figure out what the charge on the cobalt is? Okay. Sulfate, you look on the common ions list. Let's back it up just a second. Anytime you have a compound that has more than 2 elements, the first place you want to look is the common ions list to see if it has a polyatomic ion. And if you're careful, you'll find that sulfate here is a polyatomic ion. So this is our polyatomic ion, and it shows right here that it has a 2 negative charge. Okay? We have 3 of them. All right? So altogether, this gives us a 6 negative charge. Does that make sense? Okay? If this is 6 negative and I have 2 cobalts, I need a charge on the cobalt that's going to give me a 6 positive charge. So what charge on cobalt is going to give me 6 positive? 3 plus. Okay? And if you look on the periodic table with oxidation numbers, you'll find that cobalt has that choice. It can be either 3 plus or 2 plus. So I was asked to review a question in which you have to predict physical states. In this problem on your practice test, it says predict the products of the following reaction, balance the equation if a reaction occurs, and include all the physical state symbols. So in this case, I did not even include physical state symbols for the reactants. Okay, you have to figure that out. So for this first one, we've got ammonium carbonate. Okay, so I can look for either ammonium or carbonate on the solubility rules to figure out the physical states. Well, ammonium's listed in the very first solubility rule, and it says that ammoniums are always soluble. There's no exceptions over here. So this is going to be aqueous just by that first rule. Okay? If I look down here at carbonates, I'll see that all carbonates and phosphates except group 1 and ammonium are insoluble. So while carbonates are usually insoluble, they're not insoluble when they're combined with ammonium. So again, both rules tell you that's aqueous. Now some compounds don't have, you can't look in 2 different places. This is one you can't look in 2 different places. You're only going to find sulfates listed. It says that sulfates are mostly soluble. So most sulfate compounds like this are soluble. There are some exceptions. The exceptions would be calcium sulfate, strontium sulfate, barium sulfate, mercury sulfate, lead-2 sulfate, and silver sulfate. But this is not one of those exceptions. This is cobalt. Actually, it's cobalt-3. Okay? So this is going to be aqueous because most sulfate compounds are aqueous, and there's no exception for cobalt-3. Since we're on this problem, let's go ahead and predict the products now. Ammonium is the A part of this, carbonate's the B part of this. Cobalt's the A part of this, sulfate's the B part. Polyatomic ions like ammonium, carbonate, and sulfate tend to stay together in double replacement reactions. Tend to. There are exceptions, but for us in this class, we can always predict they're going to stay together. Now, when you look at a compound like this and see there's more than 2 elements, the first thing you need to do, if you don't know what the polyatomic ions are, is to look on the common ions list and identify the polyatomic ions. Because you really can't do it right until you know what the polyatomic ions are. So I'm going to look over here at the list, and just for the first one here, show you how to do that. So here's the common ions list, and I'm looking for anything that looks like some part of this formula. And I'll find ammonium, NH4, that's NH4. So I'm going to identify this as a polyatomic ion. I'm going to assume that it stays together. Carbonate is over here, right there. And so since I see CO3 here and CO3 is here, I'm going to assume CO3 stays together. And that's how you do that. Sulfate is also on that list. It tends to stay together. So A part goes with D part. So I'll put NH4 with SO4. And then I'm going to put cobalt with carbonate. And this example shows you how important it is to clearly make capital letters, and lowercase letters. Because without knowing that's a lowercase letter, you wouldn't know that's not, it's cobalt. Cobalt, any element, always is a capital letter, and if there's more than one letter, then the second letter or third letter is always lowercase. So this means that both these represent 2 different elements. Okay? All right, the next thing I want to do is to figure out what the physical states are for these compounds. So let's look, remember we said that ammoniums are always soluble. Sulfates are almost always soluble. So this we know is going to be aqueous. Carbonates are almost always insoluble. There are some exceptions, some soluble carbonates like group 1, everything in the first column of the periodic table, and ammonium. But this is cobalt. It's not a group 1 or ammonium. So this is going to follow the rule, which is insoluble, and we're going to list it as a solid. Since we have a solid over here on the right-hand side, we know we have a driving force now for a double replacement reaction. A double replacement reaction doesn't happen without a driving force. And the driving forces have to do with what we're forming. So we're forming a solid in this case, but the other driving forces for a double replacement reaction would be the formation of water or the formation of something that's a gas. Okay? Now that we've got physical states and we know there's a driving force. If there was no driving force, we just mark everything out and put NR for no reaction. But since we have a driving force, now we're ready to balance the formulas. We cannot balance the equation until we first balance the formulas. The charge on on ammonium, again, you go to the common ions list to see that if you don't have it memorized already. The charge on ammonium is 1 plus. The charge on sulfate is 2 negative. So to have a charge balanced compound, I need 2 of these, 2 1 plus charged particles to balance out this 2 negative charged particle. And so I'll put this in parentheses and put a 2 after to show that I have 2 ammoniums. If I just put a 2 without the parentheses, that would look like 42 hydrogens. And we don't need 42 hydrogens. Okay? So cobalt, we said over here, was cobalt 3. Here's how I know. Sulfate has a 2 negative charge. There are 3 of them. That makes up 6 negative charges, right? There are 2 cobalts. The only way to charge balance this is if this is 3 plus. To have a 3 plus times 2 to give you 6 plus, right? So 6 plus cancels out 6 negative. That's how we know this is cobalt 3. Well, if it's cobalt 3 over here, we're going to assume it's cobalt 3 over here. Okay? What's the charge on a carbonate? That's on your common ions list. If you don't know already, then you look it up. 2 negative. So this is 3 plus, and that's 2 negative. How many of each of these do I need to have a charge balanced compound?
2 cobalts and 3 carbonates.
All right, Paul says 2 cobalts, 3 carbonates. Does that seem right to everybody? I hope you know why, because that's important. So 2 cobalts, and 3 carbonates. Again, we have to put carbonate in parentheses because it has more than one element. If I don't put a parentheses around it with a 3 outside, it will look as if I have 33 oxygens, and that's not what I'm trying to say. So the parentheses makes it clear that I have 3 carbonates. All right, now that we balance the formulas, we can balance the equation. Remember, you cannot balance an equation without first balancing the formulas. Got it? So I'm going to let you guys balance the equation, then I'll show you the solution. We'll come back and look at it. All right. Let's go through the process here. So I've counted up everything already. I've done the atom inventory, or initial atom inventory, and I'm going to use this atom inventory now to balance the entire equation. What I find is that I've got an uneven number of, or the number of carbons is different, number of oxygens is different, number of sulfurs is different. I can choose to start balancing any one of those, but let's start with the carbon here, okay? That's just the first one on the list. To get 3 carbons on the left, the only thing I can do, these formulas are balanced. I'm going to leave those formulas alone. I can't touch those, okay? I'm only going to change coefficients, big numbers in front that changes everything. So I'm going to put a 3 here, and that's going to change the number of nitrogens, hydrogens, carbons, and oxygens. And I immediately mark those out so that I won't forget to go back and balance all those, okay? Now that I've done that, I'm going to recount all of those. And I've got 2 times 1 is 2, times 3 is 6. I've got 4 times 2 is 8, times 3 is 24. I've got 1 carbon times 3 is 3. And the oxygens I keep up with is a separate thing because there are so many of them. So when you have elements, the same element in more than one compound on either the left side or the right side, I recommend you always write it out so you can keep up with it. Otherwise it becomes really complex and you don't need that much extra stuff to have to keep up with. Write it down. So let's see, I've got 3 oxygens here times 3 is 9. And I've got 4 oxygens here times 3 is 12. And that makes 21 oxygens that I have right now. Okay, so I've recounted all of these. Now I'm ready to go back over to the other side. I can already see I need to do something here because now I've got 6 nitrogens and only 2 on the right. So I'm going to go ahead and change this. I'm going to put a 3 here and cancel out nitrogen, hydrogen, sulfur, and oxygen and recount all those. All right. 1 nitrogen times 2 is 2, times 3 is 6. 4 hydrogens times 2 is 8, times 3 is 24. 1 sulfur times 3 is 3. And since I have oxygen in 2 different places, I'm going to write it out. 4 oxygens times 3 is 12. 3 oxygens times 3 is 9. That's 21. And it looks like everything's balanced. Okay? So can you write a complete ionic equation now from this? Why don't you try that? I'll come behind you and see how you did. Okay? Write the complete and net ionic equation for this completed balanced equation.
The bottom is the net equation, right?
The bottom is the net ionic equation. This is the complete ionic equation. So here's what I did. I looked up here and I saw that inside the parentheses I've got an NH4. If I go and look at the common ions list, I'll see that NH4 has a 1 plus charge. Okay? I know it's aqueous. This is a polyatomic ion, so this is an ionic compound. An aqueous ionic compound gets split up. This NH4 is in a parentheses. I got a 2 outside. That means I've got 2 NH4s because of this, and the coefficient 3 means I multiply all that by 3, so that gives me 6 NH4s. The 3 over here multiplies the 1 carbonate by 3, so I get 3 carbonates. Here, I've got 2 cobalts, and we've already established that as a 3+ charge. This 3 here outside the parentheses means I have 3 of everything inside, so I've got 3 sulfates. Over here again I've got 2 ammoniums times 3, that's 6 ammoniums. This coefficient 3 here means I also have 3 sulfates, and the cobalt 3 carbonate over here doesn't break up because this is a solid, so I keep it like that. And then that's the complete ionic equation. In the net ionic equation, I just keep the stuff that changes. So these things that don't change, like ammonium is the same here and here, and sulfate is the same here and here, those have a name. They're called spectator ions. They're just standing around watching stuff. They're not really participating. They're not doing anything, not changing. Only the things that change, the things that are actually in the game, get listed in the net ionic equation. So cobalt, the ion that's aqueous, dissolved in water, does get changed to this solid compound. Cobalt 3+, the 2 of them, get bonded up into this solid over here. So those all change. Those are the only ones that change. This is the net ionic equation. Okay? Any questions about net and complete ionic equations here? So the question is, will there be definitions on the test? If you look at the practice test, you'll see here's a question asking what is a synthesis reaction. You might say that's a definition question. Okay? Here's another one. What is a decomposition reaction? Okay? Here's another one. What is explain what a combustion reaction is. Explain what a single replacement reaction is. Explain what a double replacement reaction is. Now, while I'm not going to tell you, and here's one that says explain what an acid-base reaction is. I'm not going to tell you in advance what questions or even exactly what kinds of questions are going to be on the test. I only tell you that anything we cover in the unit could be on the test, including definitions, okay? But you do have a practice test to help you prepare. So if you go through this practice test 2 days before the test, so that you can come in the day before the test and ask questions, you should be reasonably well prepared to take the test. Got it? So on the practice test, there are definitions in this context anyway, okay, to help you get ready. And if we've covered anything about definitions that you need to know, well, those could be on the test. Okay? Any other kind of questions anybody has? The question is about acid-base reactions. So first let's go to practice problem number 6 on the pretest. It asks, explain what an acid-base reaction is, what its other name is, write an example of this reaction, label the parts. Okay? So an acid-base reaction for us at this point in the semester only has to do with what are called Arrhenius acids and Arrhenius bases. Okay? So an acid-base reaction is one in which you have an acid where hydrogen is on the front. That's how we identify it as an Arrhenius acid, reacting with a base which has hydroxide on the back. And the result of reacting that acid with that base is the production of water and an ionic compound that we call a salt. That gives us a new definition for a salt, one that chemists are more likely to use. A salt is the product of an Arrhenius acid-base reaction other than water. So, what is an acid-base reaction? An acid-base reaction is a reaction of an acid where you have hydrogen on the front and a base which has hydroxide on the back. I could be more complete and say an acid-base reaction for us is the reaction of an Arrhenius acid which has hydrogen on the front and an Arrhenius base which has hydroxide on the back, which then produces water and a salt. Okay? That would be the definition of what an acid-base reaction is. What is its other name? Neutralization. Okay? An example of this reaction. Well, I could just choose something really simple like hydrochloric acid and sodium hydroxide. Hydrochloric acid is going to be aqueous. Sodium hydroxide is going to be aqueous. Hydrogen goes with OH. That makes the water, HOH. That's a liquid. NA is going to go with Cl. And this is common table salt. So this is a salt that you should recognize, and it's going to be aqueous. Okay? And I've labeled all the parts, or I haven't labeled all the parts because I haven't called what these are. This is the acid. This is the base. This is water. And this is a salt. Okay? Here's another question on the practice test. What products should you expect to obtain if the reactants are an Arrhenius acid and base? Water and salt. Okay? Because we just did that, yes? Now, it won't always be NaCl. Any product of an Arrhenius acid-base reaction other than the water is a salt. So then that means that almost any ionic compound other than an oxide could be a salt. Okay? Oxides don't form a salt, but I won't get into the chemistry of why. All right? Just need to know that. Okay? Water is going to be a liquid if it's an acid base or reaction. Okay? Now in a combustion reaction, you're creating a lot of heat. So in that case, water is going to be a gas. So here's still another question about acids and bases. So this is an acid. We just identified what an acid is. We said it's a compound with hydrogen in the front, right? That's an Arrhenius acid. And a base is a compound that has hydroxide in the back. So this is going to be an acid-base reaction. In this case, this is asking you to classify this as well as do all these other things that are required. Okay? So this is happening in an aqueous environment. So we need to be able to identify, are these solids or aqueous, because there's water around. Okay? Well, if you look on the solubility rules, phosphates are going to be mostly insoluble except with group 1. Well, for us at least, we've been identifying hydrogen as being in group 1, so we call this aqueous. Now, when you get to higher level chemistry, you'll find out that certain acids are considered not to be aqueous because they're weak acids. We'll talk about weak acids in a later unit, but we're not going to ever try to identify this as being a solid. But when you get to redox equations, you will assume this is going to be a solid and not going to be aqueous. But don't worry about that for right now. We're going to just use what's here to identify it as being aqueous. All right. Hydroxides, we said, here, I'll go down here and look. Hydroxides are going to be insoluble. The exceptions are group 1, strontium and barium. Well, calcium is in group 2, so it's not group 1, and it's certainly not strontium and barium, so this is going to be a solid. Okay? Now then, let's predict what's going to happen here. The front part of this goes with the back part of this. So A part goes with D part. You have to identify the polyatomic ions. Phosphate's a polyatomic ion. Hydroxide's a polyatomic ion. You look those up on the common ions list. When you have a compound that has more than 2 elements, the first thing you need to do is look on the common ions list and identify what the polyatomic ions are. Okay? So this is a polyatomic ion, that's a polyatomic ion. They tend to stay together in a double replacement or a single replacement reaction. So the H is going to go with the OH, but the subscript 3 and the subscript 2 don't transfer over because they're not part of the formula for a polyatomic ion. This 4 is part of the formula. It moves over. But this 3 is not part of a polyatomic ion. It doesn't move over. This 2 is not part of the polyatomic ion hydroxide. It doesn't move over. So only H and OH go together on the far side. And you by now should know that's water. And if there's not a lot of heat, and there's not a lot of heat with double replacement reactions or acid-base reactions, that's a liquid. And then the calcium is going to go with the phosphate. We need to figure out the physical state for this. And we said here that phosphates are insoluble except with group 1 and ammonium. This is not in group 1. It's in group 2, we said. It's the calcium. It's certainly not ammonium. So since most phosphates without those exceptions are insoluble, this is insoluble and it's going to be a solid. So we have actually two driving forces here. Formation of a liquid, formation of a solid. Okay, so this definitely is going to move forward. All right? So we need to balance this formula. We have to balance formulas before we can balance equations. Calcium is in column number 2 of the periodic table. All the elements in column 2 have a 2+ charge. Phosphate you find on the common ions list, it has a 3 negative charge. So how many of each of these do we need? 3 and 2. But that looks like I've got 42 oxygens, doesn't it? Need a parentheses. Good job. Okay. So now we're set. Now we've got the formulas balanced. We're ready to balance the overall equation. So we list everything out, all the elements out anyway. Hydrogen, phosphorus, oxygen, calcium. And we're going to make this grid here. And count things up. Now I've got hydrogen and oxygen in 2 different formulas on the left-hand side. I want to keep up with those on the out here just to make sure I don't miss one. So the hydrogens, I've got 3 here and 2 here. 3 plus 2, that means I have 5 at the moment. I've got 1 phosphorus and oxygen. I want to count those up. I've got 4 plus 2. So I've got 6 oxygens and 1 calcium. On the right hand side, I've just got 2 hydrogens. I have 1 oxygen here, plus 4 times 2, that's 8. So right now I've got 9 oxygens on the right. I've got 2 phosphoruses. This 2 outside the parentheses applies to everything inside. 2 phosphori and 3 calciums. So when you're balancing an equation, always balance oxygen last and hydrogen next to last. So I'm not going to try to balance this or this to begin with. I'll come back to those. I'm going to start, I could start either with phosphorus or calcium, doesn't matter. I'm going to start with phosphorus. This is on the top. Since I've got 2 on the right and I want 2 on the left, I can't change the formulas. The formulas are balanced. They're set. Leave them alone. All I can do is put coefficients out in front. So I'll put a coefficient 2 here, which changes the number of hydrogens, phosphoruses, and oxygens. I'm going to mark those out right away so that I won't forget to rebalance those. So I've got 3 hydrogens in the formula times 2. I now have 6 hydrogens. 2 times the 1 phosphorus gives me 2 phosphoruses. And let's count up all the oxygens. Oh, wait a minute. I left off the hydrogens over here, didn't I? I broke my own rule. That's not good. I said I was going to add them up. So 3 times 2 is 6 plus 2. So I've got 8 hydrogens and not 6. Okay. All right. So now let's see. Oxygen. I've got 4 here times 2. That's 8. Plus 2 times 1 is 2. So that gives me 10 oxygens. Let's see what I said that was. 8. So that's clearly an 8 here. All right. Now then, I've got the phosphorus is balanced, and I want to save oxygen for last, hydrogen next to last. Let's go to calcium. I have 3 calciums on the right. To get 3 calciums on the left, I want to put a coefficient 3 here, and I need to cancel out calcium and oxygen and hydrogen. Okay? Well, that 3 times 1 gives me 3 calciums. Now let's do the oxygens. 4 times 2 is 8. I've got 2 oxygens here times 3, that's 6. So I've got 14 oxygens. And hydrogens. 2 times 3 is 6. 2 here times 3 is 6. That's 12 hydrogens. All right. So I've got the phosphoruses and the calciums balanced. Oxygen we want to save for last. Let's do the hydrogen. I've got 12 on the left and 2 on the right. to get 12 on the right, I need a coefficient 12. I mean coefficient 6 to get 12. So I'm going to go ahead immediately and cancel out hydrogen and oxygen. So that you got 2 hydrogens in the formula times 6 is 12. And let's add up all the oxygens here. 6 times 1 is 6. 4 times 2 is 8. So that's 14. And everything's balanced. Okay? Now I haven't classified it yet, because you need to make sure that you always go back and reread the question when you think you're done. We're going to, if the reactions occur, we want to predict. We just did that. Write the products. We did that. Label all the formulas. We did that. Label them for physical state to indicate the physical state. That's what it is here. Rewrite the equation. Show the. Or I got to do that still. Does it say classifying? It doesn't ask you for a classification, does it? So I guess I don't have to classify it. All right? Just make sure you're doing everything it's asking for. It does ask for a complete ionic equation and a net ionic equation. We've balanced the equation already, okay? And we're showing our work as we go. All right? Now, so let's write a complete ionic equation. Well, this is aqueous, so we're going to break it up. So how many hydrogens do I have over here? 6 here. Okay, so 6 H plus aqueous. How many phosphoruses do I have? 2 phosphoruses. And that has a 3 negative charge. I'm sorry, phosphate's what I mean. I said phosphorus, didn't I? Okay. This is solid. If it's solid, I don't do anything to it.
No.
So I'm going to leave it alone. I'm going to say 3 calcium hydroxides. Okay. Hey, this is not aqueous either, is it? What am I going to do with it? Leave it alone. Oh, that's not even aqueous. That's a solid. What am I going to do with it? So this is our complete ionic equation. Now for the net ionic equation, I need to keep everything that changes and get rid of anything that stays the same. Right? So tell me what to get rid of.
Calcium.
Well, calcium is a compound here. It's in a different compound over here. It didn't change. Huh? It doesn't do it. Yeah. Nothing changes. Nothing changed. I mean, nothing stayed the same. Everything changed, right? This calcium, yes, it's a solid here and a solid here, but it's a different solid. That makes sense? So it changed from this solid to this solid, right? Nothing changed. In this case, this is both the complete and the net ionic equation. Well, you got to label which one's which. Okay. So this is one of those cases where if there's no spectators, so we the same equation is both the complete and net ionic equation. Okay.
The stadium must be fairly empty.
Say what?
I said the stadium must be fairly empty then.
Oh yeah. No spectators. Right. It's one of those games that they canceled because of a fight and redid the whole game without anybody in the stands because of the fight. So that happens every once in a while. It's rare, but it happens. A synthesis reaction is where you take 2 chemicals or more and put them together in one. That's all it is, really. Okay, so you can pick any reaction you know of where you take 2 chemicals and put them together into one.
Okay, so on like the test.
You could do nitrogen and hydrogen and make ammonia. You could do hydrogen gas and oxygen gas and make water. So you could do any reaction you're familiar with that is synthesis and write it down. So the one that was explained here a minute ago, was this. And we did this one in class. Of course, I haven't balanced it yet. So let's see. And without doing the atom inventory, and you should, that would balance the equation. Or we could do O2 gas plus H2 gas and make water. Okay, so you could use a lot of different, when I mean label, I mean make sure you have the physical states there. Okay? That makes sense? You know, I did not write down an explanation. I just stated it to you. If you have a question like this on the test, you have to actually write it out, complete sentences, complete thoughts.
What do you mean by what did you do?
Say what?
What do you mean by
Explain. What is a synthesis reaction?
okay.
It's taking two or more chemicals and combining them to make a larger chemical, or a new chemical anyway. It might not be physically larger, but at least it's making a new chemical. Labeling all parts just means making sure you've got the physical state labels on there in this case. Okay? You could write it as A plus B form, but that's not really an example. That's that's more of a illustrating the big idea. Okay, so really an example would actually use chemicals. Okay. All right, I was asked to do question number 11 on the practice test, and it says classify and balance the formula equation below. Label all formulas to indicate the physical state of the chemicals where needed. If complete and ionic equations are possible, write those and show all your work. Okay, well, let's start with the physical states for these two starting chemicals, okay? So we want to find if it's happening in water, and it says so here, it's happening in an aqueous environment, we need to know if this is going to dissolve, right? So where do we find that out?
Chart.
Yeah, what's the name of that chart?
Solubility.
Solubility rules. There you go. So look on your solubility rules. Look on your solubility rules. Really, I shouldn't have to tell you that. If we're practicing for the exam tomorrow, if I get out my solubility rules, or if I refer to the solubility rules, you should just get them out. They should be automatic. If I say solubility rules, you should pull that out. Okay? So look on the solubility rules, and let's figure out if sodium chloride is going to be soluble or insoluble. Anybody? It's soluble? How do we know that? Okay.
All chlorides except silver, lead, and mercury.
Okay, all chlorides except silver, lead, and mercury are soluble, and if there's water around, then it's going to be aqueous. It's also listed in the first rule where it says group 1 salts. Well, where is sodium found? On group 1 or in group 1 of the periodic table. So this is soluble for two different rules. Okay, if it's soluble, that means it will dissolve in water. If it's put in water, then it's going to be dissolved in water, and we'll call it aqueous. And it's aqueous because it's been solvated. Okay, so we're going to call this aqueous. And what about this? What physical state are we going to assign to this?
Yes.
It's a gas. It's one of the diatomic gases. I've told you before. We'll repeat it again now. Diatomic gases include hydrogen, nitrogen, oxygen, fluorine, and chlorine. Bromine is a diatomic liquid, and iodine can be a solid or a diatomic gas at room temperature and pressure. Okay, or close to it anyway. So this is one of the diatomic gases. Okay. The question is now is, what classification of reaction is it? It says classify. Single, if it's going to occur, it's going to be single displacement. Okay? How do we know if it's going to occur? What? Say it again? Look at the activity series. Single displacement reactions. You determine whether the single displacement reactions are going to occur using the activity series. And how do we use the activity series? What are we looking for?
To see
F is higher than NA.
Okay, if F is higher than Na. Really? Okay, find F on here.
It's on the little activity series of halogens.
Oh, it's down here. Okay. So what are we looking for it to be higher than on that chart? Chlorine. Okay. So it's not going to be higher than Na because it's not a metal. Fluorine is a non-metal. Okay. This is the activity series of metals here. It does include hydrogen, but this is a separate thing from the activity series of halogens. Behaves the same way, works the same way, but they're separate series. Okay? So is this fluorine more active than the element it's like in the compound? It is. It's higher than chlorine. Okay? So F will displace the chlorine. That's why we call it single displacement. So F then is going to join up with Na. Front parts always stay front parts. And that means Cl is by itself. Okay. It doesn't really matter with single replacement whether you go with the physical states first or balance the formulas first. It matters with double replacement because you want to figure out driving forces for double replacement. Let's determine physical states here. What's the physical state of this? Well, first of all, is it balanced? We need to figure that out too. It is balanced. How do you know? Okay. Na has a 1+ charge. Fluorine has a 1 negative charge. You can find the 1 negative charge in the fluorine on the activity series. Okay? But you need to be careful about trying to find the charge for the other thing on here, because while sodium is listed here, if it has more than one charge, you better check. Okay? But the one that's involved in the single displacement, you use the charge here. So fluorine is involved with the single displacement, you look for its charge here. Chlorine is involved in this, so you look for its formula here. What's the formula then for chlorine? Cl2. It's a diatomic gas. One of those diatomic gases I just mentioned. Oh, and it's what physical state? Gas. Okay. All right. And what we said, this was going to be aqueous. And we're going to put a plus sign. Now we're ready to balance the equation. So it's time for you to put together the atom inventory and balance this equation. I'll wait for you to get that done. So I've written out the initial atom inventory here, and let's go about trying to get it balanced. Let's see. We want to save oxygen for last, there's no oxygen. We want to save hydrogen for next to last, there's no hydrogen. So we can start with anything we want to. I've got 1 chlorine on the left, 2 on the right. I can't change the formula. I can't put a 2 subscript. I must only use coefficients. So I'll put a coefficient here. That changes the count for both sodium and chlorine. I immediately mark those out so I won't forget to balance both of them. I have 2 sodiums and 2 chlorines now. And I'm going to go over here and find a coefficient that's going to give me 2 sodiums now. All right, and change this, and that becomes 2 and 2, and the equation's balanced. So we've got the equation balanced. So we've written where we balanced the formula equation. Okay, that's this part. Balance the formula equation. And we've labeled all the formulas to indicate physical state. And now we want to write the complete and net ionic equations. Okay? Now, we're going to look for anything that's aqueous and determine if it's also an ionic compound. This is ionic. We know it's ionic because it's made of a metal and non-metal, and it's aqueous. So that one gets split. That's a sodium ion. The chloride ion is this. And then we write this down just the way it appears because it's not aqueous, it's not ionic, so it just gets transferred down here like that. Over here, we're going to have 2 sodiums. Well, I should have written 2 sodiums and 2 chlorines. 2 sodiums. In this case, 2 fluorine or fluoride ions. And a chlorine molecule, and that's the complete ionic equation. From that, we're going to look and determine what's changing and only keep the stuff that is changing. The sodium ion over here is still a sodium ion over here. It's aqueous in both places. Nothing's changing with sodium. The chloride ion over here becomes a chlorine molecule. So this is changing. We're going to keep it. The fluoride or fluorine molecule over here becomes 2 fluoride ions over here. We're going to keep that. And we do the same thing to the other side. And so now we've got the completed and balanced equation for this, and we've completed our complete net ionic equations, and we're done.